It is all too common that we define Sobolev spaces as a subset of functions which have weak derivatives and meet the right integrability criteria. So we casually just think of a Sobolev function as a function to begin with. In this lecture, my message will be that there is some big stuff going on behind the scenes here, and in reality, a Sobolev function is really just a pair consisting of a function and its derivative, and not just the function u itself. There is some loss of information going from the pair to just the function, but it happens that in the standard setting, this lost information can be recovered. If you know the function, you can build its gradient. We will see that when you change from Lebesgue measure to some other measure, this does not have to be the case any longer. To set the scene, we will have a measure that is Borel, so that continuous functions are measurable on Rn, and let's say that this measure assigns positive and finite value to balls, just so that it's not a crazy measure. Also, we can assume, if you want, you can assume that this u is absolutely continuous with respect to Lebesgue measure, so that it actually comes from a weight. So a non-negative real valued, almost everywhere finite function integrated against the Lebesgue measure. So if you want, you can assume that, optional. Now, how do we construct Sobolev functions on the space Rn with its usual Euclidean distance, but equipped with this measure mu rather than the Lebesgue measure Ln? One of the constructions is very simple because of appeal to some abstract function analysis stuff. So what you do is you define a norm on C infinity functions. So if you give me a C infinity compactly supported function, then I define a 1p norm on it by having the norm, and all these norms will be with respect to measure. So this will be integrating phi absolute value to the power p against the measure d mu on all of our n, and then you take root p. So the 1p norm will be norm of a function plus norm of its gradient, and this is in the very, very classical sense of calculus 1. The space, Sobolev space H1p with respect to this measure. So is the completion of C infinity 0 with respect to this newly defined 1p norm. That's a standard definition also used in Euclidean standard with the Lebesgue measure case. Okay, now the first question is, are creatures in the space functions, right? So this H1p is my Sobolev space, but are the elements in it actually functions? And for that, let me give you a heuristic answer as why this is the case. So what is completion? What is an element in H1p? This is an equivalence class of Cauchy sequences, right? That's what completion means in function analysis. Completion of a normed space will be an equivalence class of Cauchy sequences. So if this guy is here, then there exists some sequence phi j in C infinity 0 that is Cauchy in this 1p norm, and it represents this object U. Okay, this is one, but there are possibly many other sequences doing that. For example, if you take a subsequence of these same phi j's, at least that's another way of representing this. But let's fix one representative. Now notice that if you look at phi j minus phi j prime LP norm, all again with respect to the new measure, this by definition is less than phi j minus phi j prime 1p norm. But this goes to 0 for large indices because it's a Cauchy sequence in that norm. And that implies that phi j is a Cauchy sequence in LP mu. But LP is complete. That means there exists some LP function such that this phi j LP converges to this U. We can do with the same analysis with gradients and conclude that also there exists a vector valued function V such that gradient phi j converges in LP to this V. You can easily show that this U and V depend on the representative, the element, but not on the approximating phi j. This is built into definitions. If you take another sequence that represents bracket U, the two Cauchy sequences actually come together, and because in LP, if two Cauchy sequences come together, their limit is the same. So you can see that this U and V is unique. So there is this function which takes this element in H1P to this pair U and V. Actually, you can state this more elegantly and provide an even more elegant proof by the following. So, theorem, there exists a linear isometry from H1P of mu into LP of mu times LP of mu vector valued, where we equip this side also with 1p norm. In this case, it's the taxi cab norm, so you add the norms in each coordinate. But what this isometry does is that such that, well, it agrees with this construction here, but if you want to avoid that language, we simply look at what if we took this just to be a C infinity function itself. Then constant sequence phi would be an approximation to that, and if you follow that construction, you will see that you must end up with phi itself and gradient of phi. So you can use this as a defining here. So we're using it as a defining feature for this embedding. So for every C infinity 0. So proof is just very simple. You don't need any Cauchy sequences and stuff. This is elegant proof that hides everything then. One of those abstract nonsense proofs. So you can see that the given formula defines an isometry on C0 infinity. So you first check that on C0 infinity everything is good, And because target space is a complete metric vector space, I has a unique, again, isometric extension to closure of C0 infinity, which then by definition is just H1P. And that's the end of the proof. This projection is onto the first coordinate pi 1. So in the classical theory, where this is Ln, we just identify this with this, where this is pi 1 composed with I applying to this u. Now, why is this justified in the classical theory? Because pi 1 in that theory composed with I is injective. Of course, pi 1 is not an injective function. What I'm saying is pi 1 is injective on the image of I. And for that, I have a beautiful picture. So you have LP here, and then you have LP of vector valued spaces here. And projection obviously is never injective, but I'm saying that image of I, which consists of a copy of H1P, is sitting somehow diagonal. And that, yep. So really H1P is here. And here is an isometric copy of it sitting in this Cartesian space. And pi 1 in this case, for the case of mu equal Rn, is 1 to 1. So what is the big point? The big point is that for general mu, pi 1 composed with I is not injective. So what this means in the sense of this picture, it means that maybe H1P looks like this, and then you see that there are two different elements with the same u part. Although their function part is the same, their gradient part is not. So this if you don't use this language of embedding and then Cartesian product, this becomes extremely confusing, which was the case for me. How could the same function have two derivatives? Well, the same function in LP is not equivalent to the Sobolev function. That's the point. As Sobolev functions, these are different. If you disregard the gradient part, they become the same function in LP. In LP, they are the same. As Sobolev functions, they are not the same. And this explains that in general, then, we cannot just say a Sobolev function is some u in LP with this and that. This introduces that vagueness. This does not necessarily represent one Sobolev function. This could represent two different Sobolev functions. And such examples do exist even in R1. There exists some phi j in LP of this mu such that, so there exist two actually. There is phi j and then there is phi j tilde, such that phi j's converge to a u in LP. Phi j tildes converge to u in LP also, all with the weight. But gradient phi j converges to v1, and gradient phi j tilde converges in LP to v2, and v1 is not v2. if you want to make it even simpler by subtracting here, if you call phi j minus phi j tilde as psi j, that means psi j converges to 0 in LP, but gradient psi j converge in LP to some w which is not 0. For a huge class of weights, so that means measures that come in this formulation, the gradient is unique. And that class includes AP weights, if you are familiar with that. And then there is a very important result due to SEMS that if mu is doubling and supports Poincare inequality in precise sense, then gradient is unique. In the modern terminology, this means for P admissible, so includes P admissible weights. So for P admissible weights, this uniqueness of gradient does hold. And again, in all of these situations, then we can identify U with U after all, because this projection is one-to-one. If you want to read more about this, then I would recommend the book by Bjorns, The Nonlinear Potential Theory on Metric Spaces.